besoin de ça. Voilà. Okay, so thank you all for attending this Minerva seminar. For the seminar was starting again for this year in peculiar condition, I will say, but still it's nice to have so many of you today. So as Philippe said, but I will introduce me again because it was not recorded before. So I am David Cornu and I am starting a postdoc position at the LERMA. I have started a few weeks ago. And today, as an introduction about me, I will talk about the work I have made in the past few years in the Besançon Observatory for my PhD thesis under the supervision of Julien Montillot and Annie Robin. So I will talk about the subject of modeling the 3D Milky Way using machine learning methods with Gaia and infrared surveys. So this presentation will be split in 3 parts. First, quick general astronomical context introduction, and then 2 parts about 2 different scales. The first one about young stellar objects classification, and a second part about 3D extinction map reconstruction for the Milky Way. So first, as you all know, there is a wide variety of galaxy morphologies. So the question here is to know which one corresponds to the Milky Way. And you can see that this morphology are characterized by strong features. So for example, a barred-centered galaxy or spiral arms that can differ in shapes and number. So here, an arm in a galaxy will be a dynamical compression zone, which is traced by dense interstellar medium and by young and massive stars. And we can oppose 2 main views for galaxy structures. A more grand design view, which correspond to well-defined and narrow spiral arm structures, and a more flocculent view where we have bridges and gaps between those arms. So since we want to study mainly the structures of Milky Way by looking at these arms, I want to highlight the fact that there is a strong interplay between the interstellar medium and stellar populations inside galaxies, and especially inside the Milky Way. And it takes the form of a cycle. So I will start at the top left part with diffuse interstellar medium that is compressed dynamically to create star-forming regions, inside which a star will be born, and then they will evolve through time until their death, where they will give back matter and energy to the diffuse interstellar medium around them in the form of a feedback process. So what is interesting here is that by studying one side of this cycle, we can put constraints on the other side, and you will see that in this presentation I will talk about 2 different applications that are interested, that are focused on each of these sides. So the question is, what is the structure of our own galaxy, the Milky Way? So you may have encountered this view, this artistic view of the Milky Way, which represents what could be a face-on view of the Milky Way. So the sun is at the bottom here and the galactic center is here, and we have very well-defined spiral arms. So this is very an artistic view, so it's not something that is strongly constrained actually by observation, and this is due by the fact that we occupy a peculiar position inside the Milky Way because we are inside the disk, and the view we have of our own galaxy look more like the figure you have on the right. So what real observation from our standpoint look like for the Milky Way is more like this, with a bar in the sky. And you can see here the 2 main difficulties we will have to reconstruct the 3D structural information of the Milky Way. The first one is that there is a lot of obscuring coming from the interstellar medium clouds, and also there will be a lot of confusion, especially when we look at the center of the Milky Way, between stars that are adjacent in the same line of sight. So those are the two main difficulties that made the reconstruction of the distance structure of our Milky Way difficult. So here I have overplotted over this artistic view actual astronomical constraints that we have about the spiral arm structures in the Milky Way. And you can notice two main things. The first one is that there is a lot of unknowns. So some of them are easy to understand. For example, when we look at the other half of the Milky Way, which is behind the galactic center, it is obviously far away and behind the galactic center, so it is difficult to observe and it is difficult to have constraints for this part of the Milky Way. We have just parts that are too far away, for example, behind the Carina arm, and some of them are more difficult to understand. So for example, we have here a lack of constraints for part of arms that are really close to us, but this is due to very peculiar condition of observations here, because we are looking toward the galactic center. And another important thing here is that we have observed that there are substructures in this global view, because we have observed gaps and bridges inside the arm of our own galaxy. So it asks the underlying question, is our Milky Way truly a grand design galaxy, just like this artistic view suggests? So I will have a few words about the Gaia mission. I think you all know already about it. So this is a space telescope that measures the distances of the stars inside the Milky Way using the parallaxes. And what is new with Gaia is that it has measured those distances for a lot of stars, with 1.6 billion stars with distance measurements. And also it has an unprecedented distance range for a Milky Way survey. So you have here on the figure of the left a footprint of the distance measurement of the Gaia mission. So this is a really groundbreaking mission for Milky Way structures studies, and as you will see, it will also help us in our approach. And the other thing that is important with Gaia is that since it is a very large data set, it is one of the first astronomical surveys to enter what we call the big data era, which means that it might require sophisticated statistical tools like machine learning, for example, to perform large-scale data analysis. So I will have a few words about machine learning and why it is interesting for astronomy. So here is a very general definition, which is that it is every method that extracts statistical information about a data set and adapts the response accordingly for a learning process. So this is a very large definition, because those are very generic methods that can be applied to a very wide variety of subjects and studies. So it can be used for artificial intelligence, it can be used for computer vision, numerical science, and obviously for data analysis, which is what is interesting for us. So it has a few interesting properties. The first one is that it is able to handle fairly well high dimensionality. It also handles well a very large data set, and actually it requires very large data sets in order to work appropriately. And the last one, which is the most interesting for these studies that I will present to you, is that it is able to combine heterogeneous information in a very efficient way. So as for many other fields, machine learning has been increasingly used in astronomy. So here are a few examples. So you might all have heard about galaxy classification using deep learning, for example, but it is also used at smaller scale. So for example, to identify turbulence regimes for the interstellar medium in the Milky Way. So for the rest of this presentation, I will be splitting it in two main parts for two different studies, both aiming at reconstructing the structure of the Milky Way. So the first part will be about young stellar objects classification, where we will look at molecular cloud scales, and we will need to identify individual stars for this. And you will see that it is an indirect structural tracer for the Milky Way. And for this part, we will use relatively small dataset size with low dimensionality, so I can stick to relatively simple machine learning methods. While in the second part, we will look at 3D extinction maps, so it will be about large galactic scales by using a statistical stellar representation. And in this part, we have a much more direct structure information about the Milky Way, and we will need a large dataset, high dimensionality, and obviously much more advanced machine learning methods. And you can see that splitting this presentation in two parts allows us to both separate the physical scale and the method descriptions toward simple and then more advanced methods. So I will start with the first part about young stellar objects classification. So I will define what is our object of interest, the method that we used, which is based on artificial neural network, and then I will explain how we constructed our data set, and finally I will present you some results of this young stellar objects classification. So first, why it is interesting for us. So as I said earlier, young stars are formed, every stars are formed in dense interstellar environment. So it means that looking at young stars means looking at stars that did not add a lot of times to go away from their star formation position. So if you map young stars in the sky, you are actually mapping active star forming regions. And if you combine this information with the fact that the large-scale structures of the Milky Way, at least for the interstellar medium, are traced by active star formation, and to the fact that Gaia provide distances to individual stars, it should mean that WISO can be used to directly trace the Milky Way large-scale structures for the ISM. So the first thing to do is to identify young stellar objects. So usually they are identified and classified into evolutionary stages using what we call the infrared spectral energy distribution, which is simply the energy as a function of the wavelengths. So this evolutionary stages goes from the class 0, which is just gravitationally bound core, and it goes through the evolution of the star up to pre-main sequence object with the class 3 WISOs. And you can see that some of those classes exert strong features. So for example, the class 1 WISOs have a strong infrared excess, mainly in the far infrared regime, which correspond to the emission of the envelope surrounding the forming stars. And for example, as well, the class 2 objects shows flattened disk emission in both the mid-infrared and far infrared wavelengths. So for our studies, we choose to use the Spitzer Space Telescope. So this is an infrared facility. So we will have 5 bands ranging from 3.6 micron up to 24 micron. So I have overplotted here on each SED those bands. And you can notice a few things already. The first one is that class 0 objects are completely outside of our detection window, so we will not be able to identify those objects. And the second one is that class 3 objects will be very difficult to separate from more evolved stars, for example main sequence stars, because we are lacking bands in higher wavelengths. So it means that using Spitzer, we will focus on extracting class 1 and class 2 WISOs from infrared point source catalog given by Spitzer. So now, in order to classify those objects, we will rely on the classification scheme that was described by Gutermus et al. In 2009 that constructed a classification method based on straight cuts in color and color magnitude diagrams. So you have a few examples here. So the aim of this method is to extract first contaminants using these diagrams built upon the Spitzer bands. So you can see that it will be used to extract, for example, galaxies or active AGNs, chalk, and some other kind of sort of contaminants. All of them are not in those plots. And then it will separate the remaining stars between more evolved stars that will be mainly main sequence stars, class 2 WASOs that are in green in those plots, and the youngest ones, the class 1 WASOs that are in red in those CMDs. And actually, this classification that is widely used to classify young stellar objects with Spitzer has two main limitations. The first one is that there is some arbitrariness in the cut position, even if it was motivated by observational constraints and physical constraints. And also, we do not have robustness estimates using this method. So those limitations can be partly solved, at least using a machine learning approach, which will allow us to replace straight cuts by nonlinear splittings and to provide multidimensional robustness estimators for each object that is classified. So now I will be brief on the artificial neural network methodology, but I will still introduce a few things. So artificial neural networks are constructed upon a mathematical model of a neuron. So this neuron take as input what we call an input vector that will contain the different features or dimensions of a given object. And this neuron will perform a weighted sum using as well a weight vector of this input vector. And the result of this weighted sum will go through an activation function which will define the state of the neuron that can be either 0 or 1. So actually, neural networks techniques are what we call supervised machine learning methods, which means that for each object in the dataset sample, we have an associated target or label that correspond to the objects and that define the state we expect for the neuron at the end. So for example, for a given object, the state can be, the expected state can be 0, and if the neuron has one state at the end, we have to correct the neuron so that it will output a 0 the next time it sees the same object. So it can be done so by using what we call an error function, which is a very simple error in this example case. And this error is used to update the weight of the neuron so it can get closer to the expected answer the next time. And you can see that this update is scaled by both the derivative of the error, the input vector quantities, and by a learning rate that defines the speed at which the learning process occurs. So obviously, one of these neurons cannot do much by itself because it is limited to linear combinations. So we have to find a way to make those neurons work all together in the same problem solving. So the easiest way to add neurons is to add them independently, which will form what we call a layer. And you can see that in this representation, each link here corresponds to a weight, and each neuron has its own set of weight to all the input features and is activated independently. So all those neurons are independent, but you can find a way to encode this output layer in order to solve a bit more advanced problems. But again, it is just limited to several linear combinations. So the next step is to add several of these layers. So deeper layers here will take as its own input vector the output state of the neurons from the previous layers. And if you combine this kind of structures with a change in activation function, for example, for a sigmoid function. The objective is to have a continuous activation function that still keeps this mostly binary behavior. You can achieve nonlinear combination using such architecture. And actually, this kind of architecture is what we call a universal function approximator, meaning that you can reproduce any function that you can imagine using such an architecture, assuming that you provide it with enough neurons in the hidden layers. So I will add a few things since we want to perform classification in this case. So we have to find a way to encode the output of the network, and the classical way to do so is to have one output neuron per class of interest. So this is a 3-class example, and you can see that the target we want to provide to the network will be a 1 in the first neuron for the class 1 objects, and 2 zeros in the 2 other neurons. So obviously, using this kind of output encoding, a class 2 object will have a target with a 1 in the second position here. But we can go a bit further by switching the activation function of this output layer. And in our case, we use a softmax activation function, which is as well a very classical activation function, which allow us to construct a normalized membership probability to each class. So even if the labels will be unchanged and will still look like the example here, a typical output for a 3 example will be more like this one with 0.91 for the neurons corresponding to the class 1, saying that we have very certainly identified this object to be of the first class for using the network. So what is the network we used actually for this Young-Stellar objects classification? So our input layer is constrained by the problem we want to solve. So we have the input features at our disposal, and you can see that we have used the 5 bands from the Spitzer Space Telescope, and we also have all the uncertainties in the form of independent features, which raise the number of input dimension to 10 for this problem. Then we have to define the internal part of the network. So the number of hidden layers is really not an important aspect, because from the universal approximation theorem, it was demonstrated that using only one hidden layer stuffed with enough neurons, of course, you can approximate any function you want, and it's still a universal function approximator. So what is interesting for us is the number of neurons we put in the hidden layer, and we have observed that for WISO classification we needed between 20 up to 30 neurons in this network architecture. And the output layer is the one that will encode our classification, and we used softmax for this, and we have 3 output class, but I will come back to why we have only 3 output class a bit later. So I have to talk a bit about overtraining, because this is something very important for neural networks and more generally for most of the machine learning methods. And overtraining corresponds to learning specificities of the labeled dataset, and it is very similar to overfitting. So we want to prevent overtraining from happening, and the classical way to do so is by splitting the labeled dataset into 3 subsets: a training set that will be actually used to train the network, a validation set that is not used to train the network, but that is used during the training phase to monitor the training process, and a test set that is used to assess the quality of the prediction afterward. So what we look at actually when we want to prevent overfitting is the evolution of the error of the validation set and the training set. And you can see that at the beginning they are following the same trend, but at some point they will diverge, because the network will learn specificities of the training set, while the error of the validation set will rise, meaning that we have started to overtrain the network. So now I will describe how we constructed the training dataset for our Young-Stellar objects classification. So since good prediction require good training data, we wanted to stick to well-known and well-constrained star-forming regions to train our network. So we selected Orion, which was observed with Spitzer, giving us up to 3,000 of YSOs, and Orion is really the most close and most massive star-forming regions that we can use for that. Then we used as well NGC 2264, which is less close and less massive, but still has an important number of YSOs in it for single star-forming regions. And finally, we combined it with a catalog of near star-forming regions closer to us than 1 kiloparsec for a total of an additional 2,000 YSOs. So now that we have defined our region of interest to construct our training sets, we have to actually provide labels for all of these of the objects present in those datasets. So the first things to do is to filter those datasets by checking if the object has actually the 4 Iraq bands that we need for the classification, and with small enough uncertainties for each of these bands. So you can see that it significantly reduces the size of the point source catalog. So it means that we only have a small part of all the observed objects that have these 4 bands that are required to perform the classification. And then to construct our training dataset, we use the original Gutermus method, but we adapted it in order to solely use Spitzer. So this is motivated by homogeneity of our classification, but I will not enter into the details here. What is important is that we have a first classification step based on just the 4 Iraq bands from Spitzer, and then we have a refinement step using the MIPS band as well from Spitzer. And all the datasets were reclassified using this simplified method in order to have homogeneity between our label datasets. And one last point is that the original method predicts several subclasses. So we have here our classes of interest, so the youngest class 1 YSOs and the bit older class 2 YSOs, and we have several subclasses of contaminants that are excluded by the Gutermus classification. So in order to simplify the output of the network, we choose to only use 3 output class with the class 1 YSOs and class 2 YSOs, which are our class of interest, and a sort of trash class with all type of contaminants predicted as the same output for the network. But you will see that it does not mean that we have treated all those subclasses of contaminants equally to construct the training dataset, and I will discuss about that a bit later. So first, I want to present to you the results we obtain by making a very naive training, which means that we used balanced proportion for all subclass of objects in the training dataset. So in order to present to you those results, I have to introduce a way of assessing the quality of the given classification, and it can be done using what we call the confusion matrix, which has the advantages of both using observational proportion and that can provide an idea of the confusion between classes. So such a matrix will look like this. So you have as rows the genuine class from the label dataset. So all objects in this first line are true class 1 YSOs, and each column corresponds to the class in which the objects were predicted by the network. So you can see that we have 94 genuine YSOs that were actually predicted as class 1 YSOs by this network. And this confusion matrix allows us to construct quality estimators. So we have the global accuracy, which is most of the time not a good idea to use as our single quality metric. But we can also define a precision, which is like a purity rate of the prediction, and I will come back to this number here just after that, and we can define a recall quantity, which is like a recovery rate, so what is the proportion of genuine objects that are very properly classified by the network. So here what is interesting using this very naive training is that we have a very poor precision here in the class 1 WISOs. So why is it so? So first you can see that we have very good recall for all of our class of interest, because most of the class 1 WISOs are actually predicted as such, and it is the same for all the classes. So what is happening here is that we have a very strong imbalance between our class of interest and our contaminant classes, which means that even if we have a very high recall for our contaminant class, it is still not high enough so that it will contaminate by a significant margin our class of interest. So here we have just inside all the objects that were predicted as class 1 WISOs, we just have a bit more than 50% of chances that those objects are actual genuine class 1 WISOs. So this is an issue, and it can be reduced by using rebalancing inside our training dataset. So rebalancing will allow us to do a few things. It will allow us to lower the importance of easily separable classes, to increase the importance of complex classes, to prevent dilution effects for rare subclasses, and also to focus on the quality of some subclasses. So in our case, just like in any classification study, we have to put the emphasis on what is the most interesting for us, and in our case it was to have the class 1 WISOs with both a good recall and a good precision, and by good precision we mean a precision above 80%. So we have to rebalance our training dataset, and we are doing so by using a gamma E parameters that allow us to rescale all the subclasses regarding the number of class 1 objects we can have in our labeled dataset. So what does it mean in simple terms? So it means that when we use balanced proportion, we have a poor precision in our class 1 WISOs, and if we carefully rebalance our training proportion, we can achieve a much better results. But as you can see, we reach here above 80% precision, which was what we aimed at, but you can see that it is at the cost of lowering the recall of the class 1 objects. So now that we have defined the proper way to train the network, I will present you our general results. So when we train the network using the complete dataset, so with Orion and GC2264 and our census of 1 kiloparsec star-forming regions, we have those results. And you can see that despite the fact that we are classifying WISOs in a very wide category of star-forming environment, we are still achieving above 80% precision and almost 90% recall for our main class of interest with the class 1 WISOs. So those are our final results, and all those results are under review in a publication to Astronomy and Astrophysics, and it is going along with a catalog of our predicted WISOs. And what is interesting in this catalog is that we provide the membership probability predicted by the network for each of our objects in the catalog. So I will discuss a bit how those probability can be used and why they are interesting for as an addition to the original Guterres classification. So if we look at the membership probability of properly classified objects, we can see that they are all above a certain amount, especially they are all above 0.9 membership probability. But if you look at misclassified objects or wrongly classified objects, a lot of them are under this membership probability quantity. So while the membership probability predicted by the network is not a genuine probability, it can be used to, in combination to confusion matrix, to improve our results and to provide actual probability of prediction. So it means that if we apply a 0.9 membership probability threshold in our network prediction, we will improve all our quality estimators. So you can see that it is at the cost of removing all the objects that are under this threshold. But this allows us to keep only the most reliable objects. So what I mean by the network prediction is not a genuine probability, it means that by selecting objects that are above 0.9 membership probability, we do not recover objects that have actually a 90% probability of being a class 1 WISOs. If you select those objects, you have actually 87.6% chance for WISO class 1s to actually be a class 1 WISOs. And I insist on this here because you will find a lot of paper about Young-Stellar objects classification where they claim that they have a predicted membership probability that is above, for example, 95%, but if you look at their results inside the confusion matrix, you will see that it will be much lower in terms of precision, and most of the time it will be around the 50% I was showing before. And if you are more, I would say, if you go further in this direction by selecting a higher threshold, you will strongly improve all your precision and recall quantity, but again, it will be at the cost of losing a lot, in this case, half of the class 1 WISOs of the catalog. But the remaining WISOs are much better classified. So now that we have a list of candidate WISOs, we want to see if their distribution in the sky can provide us with information about the structures of the cloud. So here you have our prediction with an airshell background. So you can see that as we expected, all the class 1 WISOs that were predicted follows very well the dense regions of the Orion filaments. And if we look at the class 2 WISOs, we have a much higher spread. But if you look at it in terms of class 2 density, they still follow pretty well the star-forming regions, the active star-forming part of the cloud. And what is more interesting for us is now to combine it with Gaia. So in the case of Orion, it was already studied by Gross-Schedel in a paper from 2018, where they used young-stellar objects as classified by the Guterres method, using Spitzer and Thomas infrared data to do so, and they used what I call a strong Gaia selection. So they put EV constraint in terms of photometric and astrometric quantities to select the stars that can be used to reconstruct the 3D shape of the main Orion filament. And we wanted to see if our approach that provides a membership probability can help us to lighter the Gaia selection. So you can see that here we have solely applied a parallax quality selection, so with just a parallax uncertainty over parallax above 3, while here it's much more complex selection. And if we took only the WISOs which are above the 0.9 membership probability threshold, we reconstruct exactly the same trend with slightly higher dispersion, but we reconstruct exactly the same trend, and we have very, very close results to those that were predicted in the paper from Gross-Schedel, which means that properly selecting young-stellar objects with this membership probability can allow us to have more stars to reconstruct the 3D shapes of interstellar medium clouds. So here a quick summary of this first part. So we constructed a neural network WISO classification. I explained that we developed a methodology to mitigate the strong imbalance that we observed in this case, and that we added a multidimensional probability prediction for each object. And this catalog can be used to assess at least cloud distances and in some case some 3D substructures, like in the case of Orion. And obviously there is a lot to be improved in our approach. So one thing that we want to try is to find more robust labels. So this would allow us to completely get rid of the Gutermus classification to define our training data set. So for example, we could use other observational constraints or simulated WISOs, and it will allow us to construct certainly a better infrared Spitzer classification. And one other thing we want to investigate for this study is to use more advanced machine learning methods, and especially semi-supervised method, in order to reduce the bias that can exist in the class definition. So now I will switch to the second part. Which is about 3D interstellar extinction map. So again, I will describe the object of interest, our methodology to do so, the construction of our data set, and I will finish by presenting some results we had. So extinction is the combination of absorption and scattering of the light due to interstellar medium. So if we have a source of light, it will be reddened and fainted due to some interstellar medium structures. So this extinction varies as a function of the wavelengths, as it is illustrated in the equation here, and it allows to define what we call an extinction curves, which correspond to an underlying dust distribution. And in our case, for the diffuse interstellar medium in the Milky Way, we can consider that this extinction can be characterized directly by the reddening, the observed reddening of the light. And this reddening can be used then to trace the dense structures of the interstellar medium to reconstruct the global 3D shapes of the interstellar medium. And I will add one thing here that is useful for the next slide, which is that you can see that we have less extinction in the near infrared, meaning that we can have greater star distances through the interstellar medium by using infrared. So actually, extinction maps are not new, and they are studied since a couple of decades now. And it has been done so by using different methodology and different surveys. So we have here, for example, a map that is using the map from Marshall 2020 that is using 2MASS and the Besançon Galaxy model. And we will focus a lot on this map because we will use the same data. But some of those maps also use Gaia, they use sometimes Apogee and other survey. And one thing that is interesting here is the distance, the maximum distance prediction of each map. So you can see that the Marshall map can predict extinction up to 13 kiloparsec. While the maps that are combining infrared data with for example, Gaia wavelengths in the observable wavelengths, they are limited to, here in this case, 3 kiloparsec maximum distance prediction. And here you have the map from Green, for example, that is limited to 2 kiloparsec prediction because it is using a combination of 2MASS in the infrared, but with Gaia and pan-stars. And the other thing that is interesting by looking at all those maps is that some of them have been using machine learning at least as a subcomponent of larger analysis. So this is the case of those two maps, for example. But at these days, there was no extinction map that was constructed using neural networks, and especially no map almost no map is using machine learning methods as an end-to-end extinction map reconstruction method. So now I will describe the methodology we developed to reconstruct interstellar extinction map using convolutional neural networks. So we will want to have a per line of sight approach, which is fairly common in the map I have shown you just before. So it means that we will use several stars at the same time, and all those stars will be reddened and fainted according to the cumulative extinction in the line of sight. So it means that we want to reconstruct, for each line of sight we can construct in the Milky Way, an extinction profile that can be seen either as a cumulative extinction as a function of the distance, or as a differential extinction profile that allow us to relatively accurately place extinction peaks at given distances. And what we want to use to reconstruct those extinction profiles are obviously observations, and in our case, in Besançon, we had access to the Besançon galaxy model, which is a Milky Way model that can be used as an additional information with the observations. And since we want to do this with two mass observations, for now our case is identical to the approach of Marshall, at least in terms of data, and it will be very interesting to compare our approach with the results obtained from the Marshall maps. So I will have a few words about the Besançon galaxy model, which is a stellar population synthesis model of the Milky Way. So it is based on 4 distinct populations, a thin disk, a thick disk, a bulge, and a halo. And this model is constrained by observations and theoretical constraints. So for example, you have stellar evolution models inside, and you have large-scale dynamics of the Milky Way. So the prediction of, or the output of a Besançon galaxy model prediction is a list of stars with observable quantities. So for example, magnitudes, parallax, or other quantities, velocities, ages, and so on. And since it is only a statistical representation of the Milky Way, it means that we have to compare large enough part of the model to the observation in order to perform comparison, because it is only realistic if we took the result from the BGM as a statistical quantity. So one of the representation we can use to do so are obviously color magnitude diagrams again, or if you want, for example, to compare to Gaia observation, you can construct G magnitude parallax diagrams. So those are just 2D histograms of the stars that are either observed or predicted by the Besançon galaxy model. So we can use the Besançon galaxy model to predict extinction. So here on the left you have a CMD of the Besançon galaxy model without extinction. And if you compare it to the same CMD for the same line of sight using observational quantities, you can expect the difference between the two to be due solely to the extinction, if we assume that the Besançon galaxy model is perfect. So it means that the difference between these two diagrams encode the extinction profile, and this is what we want to reconstruct. And the question is why we want to use machine learning to perform this comparison. The first reason is that it allows us to have no assumption on how to make the comparison, while many other approaches have to construct a comparison method. And it allows us to combine heterogeneous surveys, and I will come back on that later when I will talk about Gaia as well. So actually, those CMD, which are 2D histograms, can be considered as images, with the pixel values being the number of stars in a given bin. And our objective here is to convert a specific pattern movement observed between the two diagrams into an extinction information. And it is very close to what is called pattern recognition in machine learning, so we should be able to use methods that are applicable to images to this problem. So in the case of neural networks, they can be specialized for pattern recognition. And for this, we have to define what is called a filter, which will apply a transformation to a subpart of an image. And those filters can be combined into a convolution operation that will apply those filters to all the subregions that can be constructed inside an image. And it means that using this convolution operation allows us to both construct transformed images, or it can construct maps of specific patterns. So in order to add this convolution operation inside neural network, we have to create what we call convolutional neural network, which are based on what we call the convolutional layer. So those are much more complex architecture, so I will not describe them here. But what is important is that those convolutional layers are specialized toward information distribution and redundancy of the information inside images. And those convolutional layers can be stacked on top of each other, just like we did for classical artificial neural networks, in order to construct more and more complex pattern inside an input image. And at the end, it is usually connected to a much more classical neural network architecture. And since those are much heavier architecture, they usually require dedicated hardware and dedicated software. And in our case, we fully coded our own framework for convolutional neural networks that are able to be trained on GPU, for example, or CPU if we want. So now I will explain how we constructed our training dataset for this study of extinction map of the Milky Way. So I will try to describe the global methodology here in a few steps. So first, we start by generating what we call bare CMD using the Besançon galaxy model for 2-mass data, or for data that will correspond to 2-mass observations. Then from this bare CMD, we will generate a mock extinction profile using Gaussian random fields. And this profile can be added to the star list given by the Besançon galaxy model in order to create a modeled extinct CMD. So we have an extinct CMD that can be used as input for our network, and we have the corresponding extinction profile that should be reconstructed by the network as its output. Then, once the network is trained using this modeled CMD, we can switch to use actual observed CMD, and the network should be able to predict the actual extinction profiles that correspond to this input observed CMD. So usually CNNs are used with what can be called conventional architecture. So it means that the number of layers, the size of those layers, and the activation functions are all already defined. But in our case, this architecture were relatively inefficient. And this is due to some peculiar properties of CMDs as input, at least for extinction, which is that the pixel position encodes the amount of extinction, and the pixel values encode the distance of the extinction. And in our case, we observe that two deep convolutional architectures seems to erase the distance information. And we explored a lot of architecture, a lot of conventional architecture as well, and our best performing architecture looked like this, with a single small convolution layer just after the input CMD, and quickly we connected to large dense layers of classical artificial neural network. And this, as you will see, work well to reconstruct the associated extinction profile from a given input CMD. So those are typical network prediction using the modeled extinct CMD. So we have here the target profile, which corresponds to the dashed black line, and the prediction of the network is in the form of a 2D histogram in the background. So you can see a few things here. The first one is that in terms of position, we are always relatively accurate, which means that every time there is an extinction peak, we mostly reconstruct as well an extinction peak. While in terms of value, it works relatively well for close regions, so up to, I will say, 5 up to 6 kiloparsec, it works relatively well. But if you look at distant extinction peaks, it will most of the time under-evaluate the amount of extinction. And when we have secondary or tertiary structures, it will as well underestimate the quantity of extinction. So now I will present some of the results we obtained with this method for actual observational data. So we focused our first results on the Carina arm tangent region. So this was motivated by the fact that this is a pretty simple region, and it has the advantages of having both dense interstellar medium structures and very empty regions as well. So it is a way to evaluate if our method can both detect relatively high extinction and no extinction. And since we are looking toward what should be an arm tangent, we wanted to see if our method can reconstruct this tangent and place it where we expect it to be. And you can see that we will generalize over a large galactic region. And this region will be split into 9 lines of sight for training the network. So each of these lines of sight used for training will be given 200,000 examples. So it means that our final training data set is composed of almost 2 million objects. So actually, since we want to find a way to mutualize the information between sight lines, because we could have trained 9 different networks for this 9 reference line of sight, but it will be very inefficient. So we want the network to train all those lines of sight at the same time. So it means that we have to find a way to give the network an information about which sight line it is looking at. And it can be done by showing at the same time for each object both the bare CMD from the Besançon galaxy model, which encode the reference line of sight, and the corresponding extinguished CMD. And these two information are considered as features for the same extinction profile. So now we want to look at our results. So to do so, we have to define references. So the first thing we wanted to see was that if our cumulative extinction in the plane of the sky was properly reconstructed. So as a morphological reference, we selected the Planck dust emission because it is a good proxy for dust distribution overall. And we have traced contour of this dust emission. So those are the observation from Planck, and here is the prediction of our network for the extinction. So the red crosses here correspond to the line of sight we use to train the network, and the dashed yellow line correspond to switch in the reference CMD used from the Besançon galaxy model, used as well as input for the network. And you can see that our prediction is convincing in terms of morphology, because we have all those structures, especially these central structures, and all those small structures inside the galactic plane that are convincingly reproduced. And we have a strong contrast between low extinction regions and high extinction regions. But still, we have a few things in our predictions that are not working well yet. So we have latitude artifacts, and it is interesting to note that such artifacts can also be observed in other maps that are using the Besançon galaxy model, for example. So it might not only come from the methodology. And we have tiling effects that can be observed when we switch the reference Besançon galaxy model CMD that is used is input. But we have a lot of idea to reduce this tiling effect, which is in this case truly coming from the methodology itself. And obviously, what is more interesting is the distance prediction from our network. So this is a face-on view of the Milky Way. So the sun position is here at the center, and the galactic center is toward the right here. And this is the average extinction in a small slice of galactic plane. And you can see that we have overplotted here in light gray what is a very simple elliptical model of the Carina arm. And to have as well observational comparison, we have added in the form of red squares H2 regions that were positioned by Wei-Han in 2014. And you can see that our prediction follow relatively well both the model of the arm and the H2 regions prediction. So we are happy with this prediction because it has a few advantages. The first one is that it predicts coherent structures between line of sights, which is not forced at all in our approach because every line of sight is fully independent, and it is solely due to the network properly merging information between line of sight to reconstruct coherent structures between those line of sight. And we have this visible Carina arm tangent. We have several structures aligned with the arm, and especially what is interesting for us are those patchy structures that are missing in many other maps and that are at a high distance prediction, and they are in great agreement with several of these H2 regions prediction as well. But again, there is a few things that we are not convinced with in this prediction. The first one is that we have absolutely nothing in the low galactic longitude part for distance higher than 2 kiloparsec. And while it can be a real result, it can also be due to the fact that we do not have enough stars to constrain those regions. So more investigation has to be made for this region. And something that is truly not true in this prediction is this large artifact at 3 kiloparsec for high galactic longitude, because it is not observed in other maps, and it is highly unstable between different changes that we can make to the network. So this is clearly a remaining artifact of our approach. So now obviously we want to compare this prediction with other map, and the only other map for which we can compare to up to these distances is the map from Marshall 2020. And you can see that while we are in great agreement for some of the part of the map, especially for the first parts of the Carina arm, you can see that the Marshall map is missing all those structures we have at high distances, and it is also much more noisy than our own prediction. But you will see afterwards that we are not in agreement for some part of the map where the Marshall map is much more convincing than ours. So while the comparison with Marshall was quite fair because we were using identical data with 2MASS and the Besançon Galaxy model, if we want to compare to other maps, we have to limit ourselves to small distances because most of the other maps are using, for example, Gaia. And it is much more difficult to do the comparison because we are not using the same data. So here is what I would call the best state-of-the-art map presently from l'Allemand 2019 that combine 2MASS and Gaia data. And you can see that we are not quite in agreement with his prediction, our prediction for close distances, but the Marshall map is not quite in a good agreement as well. And in our case, we believe that while in the l'Allemand map there is a separation between those foreground structures and those secondary structures, it is likely that our method is merging all those structures inside a large extinction patch prediction here. while the Marshall methodology will tend to separate them much more than they are truly. So there is a lot of improvement that could be put in this region. And in our case, we believe that this merging of regions can have two sources. The first one being that our GRF profiles used to train the network are not realistic enough, or simply that two mass data are insufficient, and by just adding Gaia data in our inputs, those structures will separate much better. So the next step is obviously to try to use Gaia data as additional input for our network. So we wanted to use Gaia in a peculiar way because most of the other maps are performing cross-match between, for example, Gaia and 2MASS, and we didn't want to do that because the neural network architecture should be able to combine them even if they are not heterogeneous. So in our case, it means that we just want to add two new histograms, two new diagrams in our inputs, and it will take the exact same form of 2MASS with a bare reference Gaia diagram and the corresponding extinguished diagram for the same line of sight. So all those four images are encoding the same extinction profile as the output of the network. And what is interesting for us is that we have 2 times more data, but we did not multiply by 2 the time to train the network, which means that it has successfully merged some information between the 2 surveys, and it has found a way to as well merge information between different line of sights using these 2 surveys. So here are the results we are getting using Gaia, and you can see that those results are much less convincing than the one we had before. So the first thing is that we have a saturating effect at the center, and we have also less contrast overall in the whole prediction. And what is very not a good sign here is that we are missing some structures that were observed before in the galactic plane. And all those concerns are strongly confirmed by the prediction when we look at the distance reconstruction from the network. So I will not enter too much into the details here, but I will rather explain why those results and how those results can be less good than using 2MASS only. The first thing is that it should not be the case because we just have added data to the network. So in the case we add white noise, for example, with 2MASS data, we are getting exactly the same prediction. So it means that the network tries to use Gaia in some way, but it degrades the prediction. And the only reasons for the network to do so would be that we have a systematic unrealistic bias in our Gaia input. Simply, it means that our Gaia diagrams are not realistic, meaning that we did not manage to construct inputs that look like the observed diagram using the Besançon galaxy model. And looking at them carefully, we are confirming that this is the case and that there are systematic differences between the two. And it is as well confirmed by the fact that if we look at our test set, so using modeled CMD, adding Gaia improve our prediction results. So it is just a matter of making this Gaia diagram much more realistic, and this is something that we are working on. We have a lot of we add a lot of insight from many people to improve it, and we have a lot of ideas to do so. So this prediction using Gaia should be much better really soon, and we have some of them that start to look much better for certain subparts of this prediction. So in summary, for this second part, we identified that CNNs can be used to reconstruct extinction map and especially they can be used to combine the Besançon galaxy model with 2MASS and Gaia data, and that our solution, at least in the case of 2MASS data, is very competitive with other state-of-the-art maps. With mainly, we fall in the class of maps with high range prediction with less distance artifacts than other maps. And actually, we are working on reducing the tiling effect you have observed to improve our diagram realism, especially for Gaia, but as well for 2MASS. And we want to try new profile generation in order to improve the realisticness of our training profiles. And finally, obviously, we want to perform at some point a full Milky Way plane prediction in order to provide complete extinction maps. So here is just a general conclusion to remind the two subjects I have developed today, and I will be open for question now if some of you have still time for this.
Thank you, David. So if you want to ask a question, I propose that you raise your hand on the Zoom. Yes, Aristide.
Okay, can you hear me?
Yes.
Yes.
Okay, it's just about a small detail, but it's about your first part about the classifier. When you were presenting your architecture, I think it's slide 2021. There is an input on both the layer, the input layer and the hidden layer, a -1 input on your, and you didn't talk about it. So can you maybe explain why it's here?
I did not have time to dive into such details, but this is what we called, so this is this slide. So this is what we call the bias node. So it is used in order to avoid that, for example, if you have all zero input vector, it means that you cannot constrain the weight because the weight updates is proportional to the input value of the vector. So it means that you cannot constrain the all zero value of the case where you have all zero values. So this is just a way of letting the network adjust the threshold of the activation function. So for example, if you look at this activation function, this -1 value will allow the network to automatically adjust to which value it will respond. So for example, if you want it to be maximized at, for example, -4, it will allow the network to do that.
Okay, thanks.
Benoit?
Yes, I have at least 3 or 4 questions, but let me start with the first one. About your first part again.
Yeah.
I was a bit surprised by the way you chose to give as inputs to the layer both the intensity in the bands and the sigmas. Usually, people many times have figured out that, well, I found that preparing the data with knowledge of what it means improves vastly the performance of the network. And for example, when Aristide worked on a regression network, he found that first normalizing the inputs and then actually inverse weighting the inputs with the uncertainties helped improve the performances. So I wonder what drove you to this kind of unusual choice.
Okay, so
especially since with a single layer, I'm not sure how much freedom the network has to combine the error bars with the value themselves.
Okay, so this is really, I think, the question I have every time I talk about this work. And I'm completely agree with you, and uncertainty should not be used this way. The reason we add them this way, it's because it is considered as input features from the original Gutermus method. So, for example, the original Gutermus method will perform an explicit check on the uncertainty of certain objects to determine if they are inside a class or another. So since we want to reproduce the Gutermus classification that use conditions based on uncertainties, it means that we have to use them as input features. So it's just due to our choice of labeled methodology. So if we switch the label methodology, we can get rid of those uncertainty, or we can add them in a much more appropriate way.
Do you still, I mean, do you do something with the magnitude inputs? Do you normalize them in the sample? Or?
Everything is normalized. Every
Okay.
input feature is normalized independently.
Okay. Well, I have some more, but let's see if someone else has a question, and I will come back later.
Okay.
I think you can go ahead, Benoit, if you want.
Okay. Yes, I want you to expand a little bit on the third, I think, direction you want to improve for your second project, your second part.
Yeah.
The ones on generating I think absorption profiles or something like that.
Yeah.
You said that you were using Gaussian random field, and when you say that, it was just, what? Why? Because I mean, essentially, extinction is linked to density field, and I very much doubt that the gas density field in the galaxy is Gaussian.
So the main component for us is dust and not gas, but actually there is a bunch of papers that shows that Gaussian random fields are a nice way to modelize the extinction. Obviously, it can be done in much. We did it in a simple way. It can be complexified, but especially combining Gaussian random fields, it was demonstrated recently. I think it was. Was it? I will not remember right now, but I have a recent paper about multiplying Gaussian random fields to create realistic dust distribution. So yes, it's not perfect, but it's worked quite well apparently. And what I was talking about when I was saying improving this part, I was talking about completely switching the methodology, because I think there could be more advanced way to generate those profiles. So for example, we thought of generative adversarial networks.
That was my next question.
Yeah, that will be trained to learn and reproduce realistic examples of extinction profiles. So this is something that we have started to work on, but it asks a lot of new difficulties, but we definitely want to go deeper into that, yes.
And just very technically, how do you represent your profile? Is it just a pixel value along the line of sight, or is it real Gaussian components, or?
No, it's just the output layer is just 128 neurons, independent neurons. But I mean,
but they could output, for example, position and variance of several Gaussian components.
Yeah, so we do this by using dropout in the network. So for the same input, we perform like 100 prediction. So using dropouts or randomly deactivated neurons inside our dense layers, we can construct, we can reconstruct uncertainty. So the true output of the network look more like this, with an histogram of uncertainty for the profile that is predicted. So for each point, we can define an uncertainty. Yes.
No, okay, that's interesting, but it's not exactly what I was referring to. I was saying that you chose to represent the absorption profile in real space, and you could have chosen any other basis of function to represent it. You could have chosen a Fourier representation along the line of sight, or you could have chosen a fixed number of Gaussian components to build a profile or whatever. And I wondered if you looked into that.
We did not try a lot of output representation. We had a few discussions with people who are specialized in machine learning and deep learning, and they rather told us that we should encode it in the form of a classification. So instead of having each neuron performing a regression, we should have steps. And this was the main advice to simplify the problem we want to solve, given by people who are specialists of this. But yes, we could
maybe they tell you. I'm not sure I agree fully with that. I mean, that is what they are used to do. That is what they know how to do.
Yeah.
So that is what that is their counsel. But in physics, I mean, we do really need to use regression instead of classifications if we want to improve the use and widen the use of neural networks. But whatever, that is a very personal comment.
But
I may be wrong.
The main idea is that we did not have time to try several output encoding ways. So this is definitely something that should be investigated, because maybe there is something more interesting to do with that.
Anyway, it's very easy to underestimate the amount of time it takes to test all of those. And having done two such investigation is already quite impressive.
Yeah. I mean, one thing that we want to try at some point will be to have only one neuron as output that will predict the extinction, and to have the distance as an input of the network. So it means that we could have an arbitrary resolution when we reconstruct the profile.
Mm-hmm.
And this is something that we really want to investigate as well.
Yeah. So you ask the network only for one value at a given distance.
Exactly.
And hope that in this way it would be more accurate.
Yeah, the issue is that it's much more difficult to construct a computationally efficient architecture that works this way. But we want to look into that as well.
Okay.
Any more question? David, maybe about the data, have you thought about using the H1 observations of the gas, for which you may have the distance as well?
Yes, I would say the reason we stick to those data was really pragmatical, because it was the subject that was submitted to the CNES who funded this PhD. So we wanted to focus on making it work with Gaia, but obviously one of the strengths of the methodology itself is that you should theoretically be able to combine any kind of data you want as input channels. So we definitely want to add some other kind of information. So for example, information from Herschel or any other kind of information, other surveys or everything like that. So at some point, I think we will have many input channels, and we will study which one is useful, which one is not, and which combination of input channel is the most interesting.
And I have another more naive question about your first topic. When you describe the classification, if I understood correctly, you use the classification from the Spitzer band to do your labeling.
Yeah.
So wouldn't it be better if you have an independent way to classify the type of objects? Because finally you use to teach your network, you use the same kind of classification that is based on I mean, on the same data.
Yeah, this is my improvement points here, that we want to switch, for example, to simulations. Actually, it's been 1 year since we have data for this, and collaborators for this that are waiting for us, but we did not have time to go this way. But this is definitely what we want to do next, because it will be much better to have something completely independent to define our labels, and then to find the best infrared classifications that we can make from it.
Okay, thank you. Okay, so thank you very much, David. Thank you all for attending this seminar. And just a small announcement, next week we will have Emeric Bron from LERMA, who is going to talk about the use of machine learning and clustering, as David mentioned in his talk, for the interstellar medium. So soon we will have the title and the abstract on the web, and this will be next Tuesday, 2 o'clock. So thank you all, and see you next week.
Bye.
Bye.
Bye. Thank you.
Bye-bye.
Bye, everybody.
Thank you. Bye. Thanks. Bye.